To know a bit about your interest in science prior to your undergraduate degree. I understand that you had a home laboratory, and so I was wondering whether you had any personal heroes or any experiences that led you into your chemistry career.
That's an interesting question, and I don't really think I have a relevant answer. I just, from the beginning, was interested in science, and that goes back, just interested in things, nature in general, appreciating things. Um, I certainly started with chemistry very early on. Well, I got my first chemistry set, I don't know, when I was 10 or some young age like that, and it fascinated me. I was also fascinated by biology. Um, and I must say, if I look back many years, I would have probably enjoyed doing biology more. Uh, enjoyed in the sense that the biochemical world over my lifetime has exploded from being something that was fairly trivial in the 1940, in which very little was known besides a few basic processes. The chemistry was, again, mostly mysterious. It was very clear that the biological systems were more than capable of making very complicated molecules, and deducing the structures of those molecules, so it's pure chemistry, was very well done, and World War II transferred the expertise in doing that primarily from Germany and Switzerland to the United States, as of course as a matter of the war. Right? So it wasn't until much later, way after I got my chemistry set, that I understood or had any comprehension at all of what the biological aspects of it were. When I finally was in college, I took, of course, several courses in biology, including one that was in biochemistry. And at that time, biochemistry was taught exclusively in biology departments, and it was usually taught by biologists who knew very little about chemistry. By this time, I was already pretty good in chemistry. And the teacher that I have, who I don't remember at all, except that I constantly kept correcting him. And I remember always raising my hand 4 or 5 times during the course saying, "Sir, that carbon has 5 bonds." And to the point the guy was just furious at me. And I learned very little from this person, and that's unfortunate. It would have, if I had had a much better teacher, I would have learned a lot, I think, and I probably would have moved more into the biochemical world. So in retrospect, I think I would have profited from that. But it's taken me 60 years to realize
I see.
that.
Wow.
And while I say that to you, and we'll go into this later, I'm rather concerned that you find yourself so focused on a very small aspect of things, with, you'll forgive me to say, very little knowledge of anything else.
Yeah.
It's just my position exactly. And I didn't know what was there. And I want to caution you to be careful. Don't take the easy road. You found something that's nice, but there are other things. Okay, so we'll come back to you. When I remember doing some experiments with biology. At the time, we lived in the country. I remember doing some minor operations on embryos and things of that sort from a local raccoon. It's quite interesting. But my memory of that is fairly small. When I was, after I'd finished my sophomore year in college, I got a job, a summer job, similar to what you've done. Um, and as it turned out, that summer job focused me on compounds that ultimately were related to Cubane. Right? And I can trace step by step the evolution of that summer into the Cubane synthesis and so on. Right? It's a long haul, but yet I know every step of it by the way and why I did something. And it all came from that initial interaction. So from that point of view, I was very lucky. And you may be very lucky because of the interaction that you've had recently that has impressed you. But nonetheless, I would be cautious of it because I left out a lot of stuff that I didn't know about. Right? And maybe had I known about it, I would have taken a different course. Who knows?
Yeah.
So as it turned out, this was a rather large chemical company, General Chemical. They taught me a great deal about chemistry, to a degree about science. It was more chemistry than science per se, because it was quite focused. They were interested. Well, let's see, if I remember correctly, your background in chemistry per se is not particularly strong at this point.
No,
But
I'm mainly in the biochemistry field as opposed
yes,
to
and of course these fields have diverged enormously, and it's impossible to know both fields. But at the time, there had been an observation that a particular organic compound called hexachlorocyclopentadiene, which in the chlorocarbon world, not the hydrocarbon world, like Cubane is in the hydrocarbon world. In the chlorocarbon world, all the hydrogens are replaced by chlorine. And in that world, hexachlorocyclopentadiene is the rock at the bottom of it, right?
Mhm.
And if you take benzene and chlorinate and chlorinate and chlorinate, that's called destructive chlorination. What you end up with is carbon tetrachloride. Carbon is taken away from the benzene, and the rest of it is hexachlorocyclopentadiene. A very interesting compound, which can be made, obviously, in very large quantities from simple components, benzene and chlorine. And it has quite a fascination in chemistry. And it was known from an earlier accidental discovery that if it was treated with aluminum chloride, it was a very complex reaction, and you ended up with a highly chlorinated compound, obviously, whose structure was contested for a long time. But it turned out ultimately to be bis homocubane. So that's cubane with two bonds broken and a bridge across each of those bonds. Right? It's a C10 compound rather than a C8 compound. And my early work was with compounds like that. And they, at that time, this is in the late 50s, these compounds were important insecticides, very important. And one of them was the only thing that was around at that time, which would kill what was called the Argentine fire ant, which was a very destructive ant. It was invading the southern part of the United States, and it was very dangerous if a horse stepped into a fire ant nest. They would sting it at such a level that they probably kill it. It was a very vicious ant, and of course, many stings, dangerous. So this was the only compound that worked, and for quite some years it was used for the purpose. It was then found that the compound itself was a very bad compound for humans as well. Um, it was a compound that was not degraded easily, and it appeared in the countryside, in the streams, and the rivers, and was ultimately banned, as are most chlorocarbons, because they are dangerous. Not DDT. DDT was banned as a mistake. So the whole Rachel Carson thing is nonsense. But these were dangerous compounds. So that's how I got started in the area. And I worked for summers, for 5 summers at General Chemical, primarily in this area. And when I went off to graduate school, General Chemical helped to support my work. I managed to convince one of the Harvard professors that I should do some work on it. We did that, and ultimately, I got tired of using chlorocarbons because their chemistry was so different than the chemistry of hydrocarbons that I decided to move into the hydrocarbons, or the hydrocarbons. And this was a good decision because it was just at the time when NMR spectroscopy was starting to come in. In fact, in my graduate work has some of the very first NMRs that were taken in the research laboratory at Harvard. And it was a good shift because what you could do with hydrogen, with instrumentation, you could not do with chlorine. I attempted at Harvard to build a device that would be similar to what NMR did, would be called the nuclear quadrupole spectrometer. And I built this in the laboratory, and the only thing I ever managed to tune into was the Boston police station. I never got anything else, never got a single signal from the compound I wanted, but I actually could listen to the police. But that's where it started.
I see, I see. And so your transition from these caged chlorocarbons to caged hydrocarbons was largely out of analytical necessity. So the fact that you couldn't necessarily analyze.
Yes, you could learn a lot more.
NMR.
You could learn a lot more. The spectroscopic techniques, which were available at the time, they were still very limited, but they were impossibly limited with the chlorocarbons. The hydrocarbons, you could learn more because, of course, there was a whole history of chemistry of hydrocarbons and various sorts of spectroscopy, infrared spectroscopy, ultraviolet spectroscopy. At that time, they were well-developed methods. And so you had comparisons that you could make quite easily. And the NMR was coming into focus. And in the next few years, the use of NMR, proton NMR, was the golden entry into hydrocarbon chemistry because it really allows you to learn things much, much more quickly than could ever be done by a systematic degradation of compounds. I mean, this was a non-invasive form. I mean, earlier, the structure of an organic compound usually was determined by degrading it in some controlled fashion and identifying the compounds that you got, which itself was a big production, and then trying to think backwards to what the initial compound was. And this was very, very difficult chemistry. And in retrospect, if you go back and read some of that chemistry, that was mostly developed in the late 30s and early 40s. Again, mostly because of the war, World War II. The stories are fascinating, absolutely fascinating. minuscule amounts of compounds were collected and their structures determined by this fantastic process of stepwise degradation and then rationalizing how you thought backwards to the original compound. This was all, most of this got started because of a strange interception by the intelligence, United States intelligence during the war, where it was found that a submarine, a German submarine, came from Argentina to Germany with a lot of cattle, bones from cattle. Actually, the original thing was just cattle organs, and at the same time, in intelligence, and it gives you a feeling for how difficult intelligence is. There was a rumor of gossip that the German pilots were taking some sort of a drug that allowed them to stay conscious when they were in steep dive bombers. Because of the gravitational forces under that circumstance are such that pilots would black out. Right? And so there was this rumor that this drug, somehow or other, came from cattle. And two and two were put together, and they got 23 in the process. And what happened was there was a huge effort in the United States and underground in Switzerland, because Switzerland was staying neutral. Right? Mm-hmm. There were a lot of underground connections with Switzerland, which was obviously on the United States side, to try to figure out what this compound was. Okay? And well, the reasons, then it gets very complicated. But I mean, such things were done that at military bases, the urine of soldiers was collected and then concentrated, and people looked to see if they could find useful biological compounds from the urine. And there are some wild descriptions of this. We're on an army base. 50,000 gallons of urine was collected, boiled down, and from which a few hundred milligrams of a particular compound was gotten. And then this vast effort to figure out without spectroscopy what these things were. Right? And this is where all of the structures of the steroids come from. Right? This is where it started. Right? And they never did find a compound that helped the pilots. Right? But later on, after the war, it was recognized that one of the compounds, cortisol, right, that pregnant women, right, their arthritis was, during pregnancy, their arthritis was diminished. Right? And the guess was made that it was cortisol that was doing it. Right? And the biologists injected women with cortisol, or the medical people, and in fact discovered that the steroid was fantastic at treating cortisol, treating arthritis. And then the cortisol initially was isolated from cattle, from the adrenal glands of cattle. An incredibly difficult process. Okay? Ultimately, it was synthesized by organic chemists, and ultimately, Merck, the pharmaceutical company, under orders from General Merck, they were pushed into synthesizing the compound commercially. And it was said that it couldn't be done because it was a very complicated compound. Organic synthesis at that point was fairly weak, but they managed to do it. Right? And once done, it was shown to be really effective. And the whole steroid industry comes from this. and all the stuff with hormones and whatnot. I'll, uh, I'll, I don't know. I have the book somewhere. I'll Xerox for you some of the pages.
Oh,
Of course,
thank you.
it's worth reading. It's worth reading because you can see uh, what was done at that time by the standards of now. It's just still fantastic, absolutely still fantastic. The techniques that were developed and so on. I think nowadays um, there's probably no laboratory in existence in the world that could redo those experiments because they're so spoiled, if you will, by the new techniques. There's no purpose to use the old techniques except to think about it. To think about it is very revealing, very rewarding. So, anyhow, that's so coming back to what else in the in looking at the chemistry of the compounds that were related to these chlorocarbons, I tried to develop stuff that was a hydrocarbon based, so I could follow what was happening. And that got me to look at the photochemistry of things where you use light to do reactions. And that led me, ultimately to the dimers of cyclopentadiene. I'm getting into very complicated chemistry now. And I started my career teaching at Berkeley in California, and my successor there, he was also very interested in these chlorocarbons because he and I had been friends. He followed up, and he was trying to do the Favorsky reaction, which, as you know, with the Cubane synthesis, is how you finally close the ring. But he was doing it on the chlorocarbons, and he didn't realize that in the mechanism of the reactions, the chlorines hurt everything because they were too electron withdrawing. Right? And we discussed this at one time, and I realized at that point, because I was in the hydrocarbon area, that I could do it on the hydrocarbon side, right, without all those chlorines. Right? And I knew how, from the research I was doing, how to put together exactly the right compound. With both the photochemical closure and the Favorsky. They have exactly the right compound. So if you go back to the first Cubane paper, the first synthesis of it, you'll see as I analyze how we managed to think of it. Right? And it was a good guess. It worked. Quite fabulously, it worked. So I made a whole career out of it, which was good.
Wow.
And it's looking back on these things. It's amusing how luck is very important in the whole thing. What is it? It's a wonderful expression, serendipity and the prepared mind, right?
Yeah.
And that's the important thing, right? Where you realize that something that you've lucked out with is important, right? And you can go further with it. And that's exactly what happened in this Cubane. So the very first time that the closure reaction was done, I was chromatographing the material, and the first compound that came off the column was a benzene derivative. Exactly what was wrong. And I could identify that very easily by NMR. And I decided to keep going on the column. And the next thing that came off was the dimethyl ester of cubane diacid. And if I had not continued, it would never have happened. It just all would have been shut down. So it was a good bit of luck. And fortunately, the NMR spectrum of that first cubane compound is absolutely definitive. There's one peak for the methyl of the methyl esters, and there's one peak for the cubyl hydrogens. Right? And that was determinant. Right? And interestingly, in the aromatic compound that came out first, which was dimethyl phthalate, it doesn't matter if you know the structure offhand, but that one has 6 hydrogens on the methyl and 4 hydrogens on the aromatic. And they're just 2 rungs, right? But the ratio was 6-4, not 1-1. Right?
Mm.
That you see in the NMR. And because of that, you just knew right away what it was. And then there was dancing in the street.
Wow.
So
How,
that's
how
how
did
it
you
all.
feel upon synthesizing a cubane derivative for the first time?
Yeah, that was it. Oh, it was quite pleasurable, I must say. Um, you have memories of various things. At the time, NMR spectroscopy, when I first did some of it at Harvard, the machines were very complicated, very difficult to work with, and so on. But everybody recognized this was a really important technique. And the commercial companies developed it very fast, Varian in particular. And they came up with a stripped down model that they could afford to sell. The big ones were very expensive. And at Chicago, we had one of the first ones. And I remember very clearly taking the spectrum, the NMR spectrum of this NMR machine, which was called at that time the A60. This was the first little NMR machine that everybody got very quickly. And I saw what was happening. And at just that point, one of my colleagues walked into the room, bringing with him the seminar speaker of the day. And that happened to be Saul Winstein from UCLA. And they asked me something, and I said, look, I think we made this compound. And I sketched out on the piece of paper that was the spectrum was coming out, what we had done. So it was a champagne night. It was very nice, very nice.
Wonderful.
That was fun. I remember that I have a picture of that scene in my mind, and you can see why.
Yeah, interesting. So I was trying to, at least with my limited organic chemistry knowledge, trying to read Leo Paquette's dodecahedral synthesis.
Yeah,
And
so that was much
and the
later.
subtitle is The Transliteration of Plato's Universe. And he seems to have synthesized it out of a love for dodecahedrane's geometric beauty. Was the geometric beauty a factor that played into your want to synthesize cubane?
Well, when you go back to these chlorocarbons that I was talking about, the cage compounds that you get from them are highly symmetric.
Yeah.
Right? And there's an intrinsic beauty in things that are symmetric. And of course, once you see one of these chlorocarbon cages, you can't think of anything besides cubane. It's an obvious thought because it's just a 2-carbon derivative of cubane. 2x. You have to make a bunch of rings to do it, but the relationship is clear. It's instantaneously obvious that that's what you should do, figure out how to get rid of the extra carbons and do it. And so there was a great driving force. And there was also the driving force that nobody believed that cubane could be made. It was generally thought that there was no way that any compound like that, even if you made it, that it would hold together, that it would just immediately decompose. And all the predictions were that that's what happened. It turned out later that it was the Woodward-Hoffman rules, you probably are not familiar with, but when they were developed, this is years later, the reason for cubane being stable, it was understood, but it was not originally. And it was very, very puzzling. And to many people, they still don't believe that cubane is a stable compound. I have lots of it, And I had some of the samples for 50 years, and they're fine. It's beautiful crystalline compound. Um, and they do exist. And even now, there's uh, there's some hesitation by many people to base their work on Cubane chemistry because of this gut feeling that the compound should not exist, even though it clearly does. I mean, there's a definite prejudice here. That's one of the two things that makes advances in Cubane chemistry happen more slowly. Is that too many people believe that it's not stable. And even though they may recognize that it's thermally stable, they don't realize that it's also chemically stable. I mean, you can put it in acid and base and many, many different conditions, and it's a rock. It's just, there are very few things that react with it. So if you make something from it, the chances are good that the structure of the cube is maintained, which is very unexpected, particularly the chemical stability. The thermal stability, you could wave your hands about because no one really understands thermal stability. Chemical instability is very easy to understand, but here it's not stable. The other thing that makes advances in Cubane chemistry happen more slowly is that people are convinced that it's very hard to make, that it's very expensive. That's all nonsense. It's very easy to make. It's made commercially in kilogram quantities. It's expensive, but it's not nearly as expensive as any of the biological stuff you're going to work with. Yeah. I mean, those compounds are really expensive, thousands of dollars a milligram. Right? Cubane is available for $50 a gram. Right? Nothing. Right? So, but people have prejudices, very, very strong prejudices, and they don't break down easily. So that's a problem.
Wow. And so what were the reactions of the people around you after your synthesis of Cubane? Were there some people that didn't believe you? Did the press cover the synthesis of Cubane?
I certainly, of my colleagues, I mean, I could see the compound. There was no problem. It was not a matter that we had made a minuscule amount. We had quite a lot of it right off the bat. So there was no question. One of my colleagues did the X-ray structure of it, so it was definite. Well, he was a very good friend, Emily Fleischer. He's still around, my age. And I never really understood how X-ray crystallography worked. I mean, I knew the general principle, but not the specifics of it. And he would always tease me that he found one carbon and then just reproduced the others by a mirror because of the symmetry. So one carbon was here, there had to be one there, and so on. And he always joked with me that he never really found all the carbons, he just did it in the magician fashion, which of course is not true, but it scared me initially. So the only thing, there was a chemist in England, Chapman, who after we made the compound very early on, he wrote me that he wanted me to send the details of how we did the synthesis because there were certain things he wanted to investigate. Right? This bothered me very much because there was one of my colleagues wanted to do exactly the same thing. Right? This was investigating substituent effects on the acidity of Cubane derivatives. And at the time, it bothered me, and I wrote him back, and I said, no, he just wanted to jump in on our discovery, and I didn't like that idea. And so he reproduced the synthesis with a great deal of trouble. He published the synthesis in a very critical fashion, saying that they had trouble with this, trouble with that, this didn't work, and so on. But the fact of the matter is, at the end, he got the compound. Um, Even though if you read the early part of the paper, you would think that he was just saying it doesn't work. Right? But it does work by using exactly the same chemistry. And one of my colleagues was more upset about this than I was, that he purposely reproduced the whole synthesis and published to say that Chapman's what he was saying was nonsense. Right? That it was nonsense. But it turned out, and again, this is a matter of luck, that the way we got the starting materials for the compound, the C5 compounds, the cyclopentane compounds, we did it in a way that was straightforward for the time, but Chapman, using another aspect of our chemistry, which had nothing to do with this, but just using a different aspect of the chemistry we had discovered, found a very simple way to make the necessary starting materials. Right? And that changed things enormously. That was a very, very important discovery that he made. How he made the discovery, I have never understood, nor did he, because it involves such a change in solvent. It doesn't work in tetrahydrofuran. It works beautifully in dioxane, and very similar compounds. But that was very important, and certainly it's one of the reasons that Cubane Cubane compounds can be made in reasonable quantity. Without that change in the early steps, it would still be very difficult. Now, I think that change would have been discovered by others without much trouble, because it's fairly simple chemistry. But as luck would have it, he found it, and he found it because I forced him into it. So again, luck helps.
Yeah.
And then, what can I say? So it was generally accepted. I lectured all over the place about it. But at that point in time in synthetic chemistry, making highly strained compounds was a very broad goal. Many, many chemists work with cyclopropanes, cyclobutanes, with polycyclic chemicals, and with highly strained. Cubane, of course, is one of the most strained of the compounds. And there was a lot of question of how can you make these things? And most of the highly strained compounds, there were few that came from nature. Actually, nature makes some cyclopropane compounds naturally. That at the time were fairly tough to make in the laboratory. Nature did it. Nature never made a Cubane, as far as I know. But the push at that time was to make more of these compounds, this kind of compound. Now, Cubane is called tetraprismane. It's four-membered rings, and it's a prism, in that the corners are opposite. It's an Archimedean prism. The next step up of regular prisms is pentaprismane, where the two faces are five-membered rings, and then you have five four-membered rings fusing those together. And so that was the next thing we tackled, right? Rather than looking at the chemistry of Cubane, we focused on the synthesis of the next one in the series, because we were also very interested in comparing properties. Remember, at this time, no one understood why Cubane was stable. So making the next one to see if it was stable is important. And we focused on that, and we were successful. It's a harder compound to make, but we certainly made it. It has not found much use because it is harder to make. And then we tried hexaprismane. That's two benzenes fused with six cyclobutanes. That's never been made. Enormous effort has been made to make that compound and to discover its relationship to benzene, because it's very, very highly strained. Benzene, of course, a very stable compound. So getting from it to benzene is a very interesting question, but it's never been made. We then moved to the next regular solid, which is dodecahedrite. And we worked for a long time on it, and I'm sure you've seen the published papers on it. I know at the time, Leo Paquette, a very good friend, and I competed on that. He won. But interestingly, with great, his work was very, very good. I have great respect for him. Unfortunately, he's passed away. But I'm about the only one that has really defended his synthesis, because at the very end of the synthesis, it requires a treatment with acid, right? And the system doing something that you really can't predict is going to happen and look that, right? And a lot of people dismiss the synthesis because of this, that it wasn't planned. And that's quite foolish. I mean, you should certainly take advantage of anything that happens that's in your favor, which he did. It was a very good synthesis. I remember very much when we first did the Cubane synthesis, most of the highly strained compounds at that time either were the cyclopropanes that appeared in nature or compounds that were produced in what I would call magic reactions. When I was a kid, besides for Superman in the comics, there was another hero called Captain Marvel. And Captain Marvel was in his real world was Billy Batson. And Billy Batson, when he wanted to save the world, would say, Shazam. And there would be a big bolt of lightning, and he would be transferred from being this little twerp to being Batman, not Batman, Superman. No, I'm sorry. Captain Marvel, Captain Marvel. Had a big M on his thing. And I insulted a lot of people when I talked about the synthesis of Cubane, because the synthesis of Cubane, if you read the initial paper, every step was planned out in advance. There was no need for Shazam. Whereas the other compounds that had been made and the ones that people were making all had this Shazam quality to them. You see. That basically they fell out of the pot and no one realized why. And I sort of got up on a soapbox and I lectured people that it was time for chemistry to get away from Shazam chemistry and get on to planned synthesis where you had good reason to believe something was going to happen. And you didn't need an act of God for it to work. So there are limits to luck as well. You can't depend on it all that much. So there we are. Now at that point, we will focus very much on the chemistry and the synthesis of these other compounds. And we pretty much left Cubane chemistry. And the reason is actually very subtle. The entry point into the Cubane system has two carboxylic acids on it at opposite corners. We learned how to take those off and replace them by hydrogen to give Cubane itself. But we didn't really know how to make other Cubanes. Okay? After all, you have 8 positions on Cubane, and you wonder, well, how do I put the methyl group here? Or, you say you want to make alkoxy Cubanes. How do you do it? At the time, nobody had any idea that it could be done. And here you were dealing with a system whose stability was always in question. So for a while, we left the problem. And then, let's see, coming back in history, I was visiting at Callister University in Canada. And there's a lovely guy there who also has passed away, Vic Sneakus. And he was looking at the activating positions in benzene with an amide group. I had not heard of this before. I was very bad at following the literature. But halfway through this conversation, I realized, oh my God, this is the way to do it in Cubane, because the hydrogens of Cubane and the hydrogens of benzene are closely related to one another in their structure, bonding. I went back and we tried this and it worked like a charm. And from there on, we knew we could make any Cubane that we wanted to. I just opened the door completely. And at the time, the people I had worked with at General Chemical, the head guy, had left General Chemical, and he had gone to work for one of the Army research laboratories. And he had always followed my career. And when we made the Cubane, he thought, well, if you put 8 nitro groups onto the Cubane, you would have a marvelous explosive. Okay? And since we found that the Cubane was stable, right, the Army decided to support the research. And they gave me completely free hand as to how to do it. Right? It was many, many years till we finally made octonitrocubane. And then the Army and the Navy stuck it out for the whole time, right? But we discovered all the rest of the chemistry of cubane because of this work for ultimately octonitrocubane. Now, the reason at the time that octonitrocubane was seemed to be an important compound is that the military had developed guided missiles, computer-guided missiles. At the time, again, this is many years ago, the computers that were put into the missile to control the missile were so big that there wasn't enough room left for the explosive at the other end of the missile. And so it was a huge problem. Right? You could get the TNT there, but you couldn't get enough of it there because of the requirements to lift the computer part of it. And so that's why octonitrocubane was wanted, because they thought its density would be very high, as it is. Right? And so it would be a proper substitute. Right? Well, by the time we made octonitrocubane, the computers were shrunk down, to penny size, and it was no longer needed, which was a great relief to me because I had no desire to make explosives. But we did succeed in making the compound, and indeed, it does have most of the properties that were predicted for it. But it took us many years to make it. I don't know, 20 years or more to get it. And I still have a sample of it. In fact, it's stable. You can hit it with a hammer, nothing happens. It sublimes at 200 degrees. Completely stable compound. Unlike most other explosives, which would detonate way before that. So again, the intrinsic chemistry of the cubane skeleton is very different from other compounds. Very different.
Wow.
So that gets us up to pretty much where we are. But once we discovered how to make substitute cubanes using this initial reaction, then we could make many different cubanes. And in that process, we discovered many other things that were very important, turned out to be very important in physical organic chemistry, making compounds much more strained than cubane, like the olefin cubene, homocubene, cubyl cation, all the things that nobody thought could possibly exist, but did. Um, the cation of cubane, where just one hydrogen is taken off as H minus, and you get left with a carbonium ion, C plus, at the corner. Uh, it's calculated that, how shall I put this? To get a compound like that in the classical chemistry way, that it would, should I put it here? Yes, the rate of the hydrogen coming off, leaving the cation, is calculated to be that it's so slow that it would happen. It would be twice the age of the universe before half of it happened.
I see.
That's the calculation. Right? In actuality, it happens in milliseconds. Right? And this is the largest difference that I know of between theory, calculation, and experiment. That's what we found. And this was simply, we made a bunch of observations along the way, not looking for this in particular, because we assumed, like everybody else assumed, that cubyl cation was impossible. Well, it turns out it's not impossible. It's very easy to form comparatively to other things. And this, it's one of the things that has proved a very great interest to me, in that the theory that's associated with compounds like this and the experimental values tend to be very different from one another. And there's still a big problem with this. And it's a big problem in chemistry, where being able to calculate things has taken precedent over being able to make them, do them experimentally. And the fact that the experiments and the calculations often disagree by enormous amounts doesn't seem to bother anybody. I've never understood this. I have never understood this. And you can see the problem in a much more practical way when you think about the modeling, the computer modeling of climate change, where the models are all different. There are half a dozen different models. Some are considered to be acceptable models, but they all produce different things. They don't lead to the same conclusion. Well, nobody seems to bother. They still think everything's going to fall apart. That may be that it does fall apart, but the experimental evidence is still pretty bad. No, I mean, it's quite obvious that certain things are happening to the climate. Fine. I'm more than willing to grant that the carbon dioxide levels are going up, but I'm not willing to grant that you can then calculate what the future holds. That's, as far as I'm concerned, it's absolutely prejudiced. You decide in advance what the information is that you put in, and then act surprised when you find out that the world's going to fall apart. It's not. At least I hope not.
Yeah, yeah, wow.
So the future of Cubane, well, the future of Cubane is very open. It's certainly dependent on people coming to realize that you can actually work with the compounds easily and that you can produce them commercially. Then it's a matter of looking more closely for them to be developed as drugs, pharmacologically active drugs, being developed as polymers, and all sorts of things. And in fact, this interview triggered my going to look over the last couple of years some of the things that have been going on in Cubane chemistry. I'm quite amazed, actually. I'm too old to follow it bit by bit. But it is a field that is getting larger, not smaller. And I think ultimately there'll be some very important things. there already have been some drugs that are modeled on other drugs and are better than other drugs, but not sufficiently better to justify the expense. But that, but it just means that the door is open to find other things. I mentioned to you long ago that the the cubane that's most investigated has the substituents on opposite corners,
Yes, yes.
whereas the compound that has it 1,3, which is also fairly easily available, hasn't been investigated at all. Very, very little is known about it. And it's very foolish because it is the one that has the most different geometry relative to other compounds. Right? The 1,4. The 1,4 is very similar to the benzene compounds, as is the 1,2. Right? But the 1,3 is very different. Very different. If you take the meta-benzenes, the 1,3 benzene, right, one group can't reach the other. One is pointed this way and one is pointed that way. This of substituents, right? So if it's going to bond to something in a biological sense, the binder has to be able to accept that geometry. Okay? In the cubane, the geometry is this way, right, of the substituent, which is very, very different. It makes it easy to form a bond, easy to complex with another compound. So it hasn't been looked at all, to my knowledge. So it's something to take on. The future is bright, but you have to have an open mind for it.
And I'd love to know about your opinion on the tetramerization of acetylene. Are there any labs that are working on this?
I'm sorry, say that again.
I'm interested in your opinion on the tetramerization of acetylene to produce cubane.
Oh, yes. Well, as far as I'm concerned, that's the way it should happen.
Yes.
Certainly, it's a very cheap compound. It's completely downhill to go from acetylene to cubane energetically.
Mm-hmm.
And somebody just has to discover how to do it. And if you think about it, you don't have to do it in high yield. If you do it in 1% yield, somehow, take 100 grams of acetylene, which is worth pennies, and make 1 gram of cubane, that's 1% yield. It's very low yield, but you make a very important compound very easily. And nobody figured out how to do that. Sooner or later, I presume somebody will. I once thought that I would offer a prize to someone who did that, but it's a bit too self-satisfying. But I think that's in the future somewhere. But there's more and more people are interested in doing chemistry where some molecules hold other molecules in particular positions. And because they're held rigidly in particular positions that are close and with the right orientation, you can get chemistry to happen that ordinarily would not happen. One of the ways of doing this is with high pressure, for example. And there is some very fascinating chemistry of cubane itself with high pressure, how the bonds come apart. It's very fascinating, very difficult chemistry to understand. But it's what happens. Most of what's done with things like this is you take a metal and you complex something to it, and the complex holds the molecule in a particular position, and then some chemistry can happen. That's obviously useless in cubane chemistry because what you really need is if you want a metal to do this, the metal has to end up sitting in the middle of the cube. There's no room for that, right? The metal has to bring the acetylenes together from the outside, not from the inside. That's tricky because there's not enough room for things like that. So you need a major discovery there, but it'll come, particularly if some cubane comes along that cures some disease or something of that sort. No one hopes it happens that way, not for an explosive. I don't need more explosives in my life. So, well, let's see, what am I having? Just a second.
Oh, yes, please. Thank you.
Just a second. That's some of the original stuff.
Could you move up? So, oh, wow, wow, wow. Beautiful.
Yeah, it's very nice. It keeps moving around in the bottle. It sublimes very easily. And the problem is that bit by bit, I'm losing it. Its vapor pressure is high and it escapes. And it's been a problem that I've only realized in the last year or so. And I'm having a great deal of trouble figuring out how to keep it in a bottle that I can open to get at. Right? I mean, obviously, I can seal the thing completely, just by melting the glass. Then it's stuck. um, but I see that a lot more of it had disappeared. It's very bothersome.
Wow, wow.